Hello, this is Robert Guderian. Today we are talking about numpy, our real arrays. Uh, as a reminder, this is a programming class, not a Python class. So I feel like there's some justification that's needed for why we are teaching you about real arrays. And that's because every other programming language has an array type, not a list. And because Python is nice, but Python is slow. So we need a way to go fast, and I need to show you what fixed length arrays feel like and why they're important and why they exist in computation. So lists are great. I've called them arrays. I believe I apologized for calling them arrays when I introduced them. And, well, that's because they feel like arrays. But they are stored in a fundamentally different way. Lists are stored something like this. I'm going to have my list. And that's going to be a pointer. And we know a little bit about pointers because of functions. To our first data piece of data at element 0. And that one's going to be pointing at element 1. And that one is going to be pointing at element 2. And then this will go on and on and on until our last element. This is called a linked list. This is a data structure. So there is a data structure that we don't really fully understand, and we don't have to, that is backing our lists. Okay, that's fine. Where does this fall apart? Well, I want to get to element 2. Okay, well, I have to access at my pointer, and I have to visit this one, visit this one, visit this one. That was 3 steps. What about element 100? About 100 steps. What about element 1000? About 1000 steps. Python does do some optimizations on this, but it's still not free. And this is dynamically allocated, meaning that it grows and shrinks, and Python will deal with that for us. But it also means that it can't make any decisions to optimize it right up front. And Python is an interpreted language. Well, we've seen this feature of Python already. Python, we had to write our functions first, and then we could call them. That's because Python is discovering our program as it's going line by line through our program. And it doesn't know where it's going next until it gets there. That's not great. There's no strategy. It is running lines of code, and whatever it is, it has to just take it at face value. It can't optimize it for you because that optimization might not work for what you're doing. So that's too bad. How do we get around that? Well, numpy is written in C. That's a different programming language, and it's compiled. And what compilation means is that you have a bunch of source files. They're written in a different language, and you'll send a piece of software called a compiler and say, I want to compile my program. It's going to take all of these files that are written by humans and make an executable file out of them. But it has the entire scope of the project. It knows everything that you're trying to do. It can interpret everything and put it all together. And it can leave out functions that you never call. It can say, oh, you're writing this for loop in a funny way. I can do it better like this. And even small for loops, it'll actually unroll them and just copy and paste your code for you because it's faster. And it can take all the time in the world to do optimizations because it's run once against your program. And for example, the numpy that's installed on your computer was probably compiled months ago, but we're going to be using it again and again and again. It can take 10 minutes to compile a program. It won't, but it can. And it'll be highly optimized and it'll be fast. But, oh my gosh, C isn't nice. It is what is called a low-level programming language, where you can write instructions to a single processor, saying, I know I have an x86-like processor in here. I'm going to give you these instructions because I don't trust my optimizer. Python doesn't let us do that. Python is a high-level programming language where we don't even have to declare our variables. It'll do it for us. Things will just magically happen. We have lists. They grow. They shrink. Magical. That is awesome, but it makes for a slow programming language. C takes all that away. It gives you bare bones and says, if you build it, great. If not, it's not there. So what's the trade-off? Have Python call C files. Ooh, now we write in a pretty beautiful language that we can understand, and it's easy to write, it's easy to learn, and it can still run fast. That's neat. So numpy arrays. These are not equal to lists. They have a lot in common. And again, sorry, I will say them interchangeably. But the difference is that numpy arrays and real arrays in every other programming language and on your computer are fixed length. And that feels like a step back. And we have to determine this when the array is created. Oh, that feels like another step back. I can't just add things as they come. Nope. The type. There's only one data type in a numpy array. Every single element is the same type. NumPy arrays are stored in contiguous memory, meaning it's all together in one cohesive chunk. And that's nice because it's going to let us have mathematical functions to figure out where data and information is. So what do I mean by that? And why is this good? So I've probably drawn one of these for you already, an array representation looking like a fallen down ladder. Oh, okay, that's fine. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 long, index from 0 to 8. Cool. Okay, so what contiguous memory is going to do for us, and having a single data type will do for us, is something nice. We're going to have something called an int64, and that is a 64-bit integer, which means that we no longer have unlimited length integers. Oh, that feels like a step back too. We can only have, I think it's 2 to the 63 minus 1, a very large number, as our maximum integer. Well, okay. Well, what does this give us? There must be some perks. Well, we know that each one of these bins is going to be 64 bits long, and we write that as a lowercase b. So then we'll have 64. Well, this is going to be 128, and then some other number, 256, and then another double. I don't want to calculate all the ones in the middle, but we can actually calculate where our data starts, and each one of these will be 64 bits, and that means 64 ones or zeros, and it all starts at index 0. So our computer is going to give us a start memory address, and then some contiguous memory. So we're going to view this as address 0. And then this is going to be byte 64, byte 128, byte 256. And okay, I can start to do this now. So I want to jump to spot 1, 2, 3, 4, to index 4. Well, I could just walk there, 1, 2, 3, 4. Well, that's dumb. I know exactly how many bits I need to skip. It's going to be our offset, or sorry, memory, our memory start address, which we don't really know. This is going to be some big hexadecimal number that we don't have to know. We just know that it's a number that is going to be an address in our RAM. And we really don't want to know it. But it's going to be that start address plus our offset times 64. So for example, we have some started memory address, and our offset, we wanted to get to 4 plus 4 times 64. Well, that is plus 256. And then we'll be able to jump to this spot in 2 calculations, multiplication and then in addition. So our computer's processor runs at 3 gigahertz. Say that this is 3 instructions. It'll take 1 billionth of a second. That's fast. And it'll always be 1 billionth of a second if it's 3 calculations here, because multiplying by 8 is the same math. Multiplying by 16, 24, wherever we want to jump to, we can just mathematically jump there and then step our program pointer to point at that single index that we care about. That is what is random access memory. People think random access memory is like, well, we'll just grab any one of these bins. The idea of random access memory is that I can randomly jump to any one of these cells in my array and not have to walk through a data structure 0, 1, 2, 3, 4 to get there. That is what RAM is, and that's why it's called that. We're learning about computers. I'm sorry, I'm very excited about computers. Okay, numpy data types. They're actually limited here. Oh, sorry, I'm just going to finish up one last thought. These addresses, these indices, they start at 0 because they're an offset. And I told you to imagine it as an offset. That is to get to this point where you know that an array is a fallen down ladder, and we can use the offset to calculate which bin we need to get to. It's beautiful. Take operating systems with me. I'll nerd out even harder. It's amazing. Okay, float 64, int64, bool. Bool is Boolean, true and false, which is actually just 1 bit, 0, 1. Fun fact. There is some other data types. We probably won't use them unless we might use bytes, depending on how mean I'm feeling. Because we can actually represent a letter in there and magic can happen. And yeah, there's lots of these. And including complex numbers. That's the exciting one. The idea of an imaginary number is not actually lost in NumPy, which is beautiful. But again, we're going to stick to these. I'll show you how to change the data type on your arrays if you have to. Right, so we have to declare these up front, and that is because we're creating that contiguous memory. There is an append function in NumPy. It's fake. When you append to a NumPy array, what you are going to be doing is having your old one, copying that into new space with potentially just one more spot, and then copying it. And then you'll have that new space that's now available to you. Is that a copy? Or is that actually appending? No. You are functionally, this is many, 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 many operations to do this. Based on how many cells you have. It's going to be hundreds, thousands, millions of operations. It is not free. Appending to a list is basically free. That's going to be 2 or 3 instructions, which is cool. This is that math that I showed you before. I jumped ahead. It's kind of neat. That's why we indexed at 0. The summary is NumPy is fast. We do have to know a little bit about how things work. We're not going to test you on the offset stuff. That is just justification for why these indices are 0 and why they're offsets and indexed at 0. It's weird, but it's actually an important idea. Thank you for paying attention, and I'll talk to you next time.